Hello, thank you, Dr. Ben. My name is Ikram Hassan Efaz, and I completed my PhD from the University of Texas at Arlington this May 2021 in structures and applied mechanics, and my supervising professor was Dr. Noor Yazdani. Today, I'm going to present a portion of my research, which titled Live Load Distribution Factors in an I-girder concrete bridge with excessive vibration and partial deck girder composite action. So the outline of the presentation is the introduction, a description of the bridge, problem statement, diagnostic load test phase 1 and 2, then live load distribution factors, and finite element modeling. The current AASHTO LRFD provision for live load distribution factor depend on various factors like span length, spacing, and stiffness of the girders. However, the AASHTO LRFD doesn't consider composite action between the superstructure element, so it doesn't consider the effect of partially composite deck-girder interaction. The South Highway 75 southbound bridge is in McKinney, Texas. It consists of prestressed concrete girders in 4 spans, and the total length of all spans is 440 feet. The deck thickness is 8.5 inch, consists of cast-in place deck on precast prestressed panel. And we only select one span for evaluation to optimize the work, and also that span has the maximum number of cracks and potholes. So we can see that the bridge has 11 girders, and it consists of like TX54 girders. And this is a very common scenario for TX bridges. For bridges in Texas, they use precast panel on the top of the girders, and then there is 4 to 4.5 inch cast-in place concrete. And all of these superstructure elements should be in full composite according to the design. However, the bridge was observed to have transverse and longitudinal cracking and potholes, and excessive vibration was also felt on the deck while there was traffic. So the UTA team initially visited the bridge with personnel from the Texas Department of Transportation. The bridge was built in 2011, so it's very unusual for the bridge to experience such issues because it's a fairly new bridge. We conducted impact echo and ground penetrating radar. We use those to scan the top of the bridge along the grid lines. I'm going to present only the impact echo result because that's more relevant to this portion of the research. We can see this is the impact echo contour, and the red color indicates very high possibility of delamination. So we can see that there is a lot of red colors, especially on the top of the girder lines, which are the white lines. And these delaminations seem to be more prevalent on the areas top of the girder line. So we did a diagnostic load test. The instrumentation is shown here. We used 26 strain gauges in the top and bottom of the girder, and also some strain gauges under the deck. And we use a 12 rotational tiltmeter to find the end rotation of the girders, and also to find a deflection. So static load test was performed on span 3. 3 trucks were used, and we did both crawl speed test and the stop location test. So the crawl speed test where the truck goes on the deck, and the stop location test is when the trucks are stopped at the mid of the span for 30 seconds. We did this test according to AASHTO manual for bridge evaluation. So these are the load test path that we did. Every path was run twice to ensure the repeatability of the result, and we also show the weight of the axle of the trucks for the load test. So the load test phase 1. We can see the result from here from the strain response for different paths. So, for example, for the first path B1 run 1, we can see that the truck tires are near the girder B1 and B2. So the B1 and B2 provide give us the maximum strain response, and so on. So we also calculated the theoretical neutral axis and also the experimental neutral axis from the load test, and we see that the theoretical neutral axis was for full composite action was 57 inch from the bottom according to AASHTO, and theoretical neutral axis for the non-composite girder was around 40 inch, but our experimental neutral axis was 43 inch from the bottom, which gives us a conclusion that there is a loss of composite action between the girder and the deck panel system. In order to so after a year, we conducted another load test to see the rate of deterioration. Most of the other stuff similar, so that we can compare the result after 1 year, and we can see this is the load test result from the follow-up load test after a year, and results were pretty much identical with the initial load test. However, there was only 15% composite action on average between the girders and the deck panel system, and due to possible concrete delamination and partial composite action, the lateral stiffness of the superstructure was reduced, and that's why there was excessive vibration due to the reduced lateral stiffness. So we calculated the live load distribution factor both using the AASHTO provision and also from the diagnostic load test, and we calculated the LLDF for the bending moment for the interior beams for one lane loaded condition, and we can see that the distribution from experiment ranges from 0.26 to 0.43 when the LLDF from AASHTO is 0.52 for one lane loaded condition. So the actual LLDF found from the load is varied between 0.26 to 0.43, which is about 21% to 50% less than the theoretical value. So the partial composite action in the superstructure resulted in a loss of lateral and vertical girder stiffness, which in turn compromised the girder load distribution characteristic. That's why extensive lateral and longitudinal cracks were also on the top of the deck, which supports our conclusion, and also the impact echo data where we see a lot of delamination on the top of the girder lines that also support our statement that there is loss of composite action between the girder and the deck panel system. And then we also conducted the finite element modeling. We modeled the bridge in Abacus CAE. We modeled only one span, and also we modeled 5 girders with the PCP and the CIP deck. The girders were more modeled using the solid 3D element, while the reinforcement were modeled in 2D element. So, in order to induce the partial composite action, we varied the contact properties. We induced a cohesive contact between the girder and the deck panel system, and varied the shear stiffness parameter in order to induce a partial composite action into the model. And then we compare it with the experimental strain and the rotation value from the rotational tiltmeter, and we can see that the values matched quite well. And then we found the LDF from the model and compared it with the load test and the AASHTO result, and we can see that the finite element model values are quite similar with the experimental load test value for the LLDF. So therefore, the study could be this model could be used for future retrofitting purposes, and also like this study is unique in a sense that previously there was no similar study to evaluate the effect of partial composite action on LLDF. So this study could be a reference, and in future it can be used to evaluate the effect of partial composite action on the LLDF and can be included in the codes. So this study was conducted in the Department of Civil Engineering from the University of Texas at Arlington, funded by Texas Department of Transportation, and also supervised by my professor, Dr. Nur Yazdani. Thank you, everyone. If you have any question, please feel free to ask me.
All right, thank you, Ikram. Looks like there is one question here in the Q&A box. How did you decide on the parameter that varied the partial composite action in the Abacus model?
So, okay, this is a very good question. What we did, we introduced the contact between the girder and the deck and the panel as cohesive contact. And for the cohesive contact, we changed the shear stiffness parameter. We varied those parameters to make sure that to induce the partial composite action in the model. Is that answer your questions? Okay. So I'll drop my email address. So if you have like more inquiry, just send me an email. I can discuss this with you in details. I think that will work.
Sure. We have time if you'd like to consider more questions, Anthony, or in the meantime, I have one question for you. You mentioned that this bridge wasn't very old, maybe 10 years.
Yes, sir.
But you saw a bunch of degradation. What's the future of the structure? Is there some work being done, or have these distribution factors changed the rating approach?
Yeah, so actually we also did load rating for this bridge. We combined the non-destructive evaluation testing and the load testing to load rate the bridge. We used a unique method, and we sent this report to Texas Department of Transportation. So I think they are going to decide what they are going to do. For now, like this is still ongoing.
So Ben, if you allow me to partially respond. Thank you, Ikram. Good job. So this is Nouri Yazdani, co-author of Ikram Efaz. So this is an interesting discussion. This whole concept of the PCP and then the CIP deck on top of that, and then the girder. Brand new bridge last year. I think earlier this year on I-20 near Dallas, we scanned the surface with GPR and impact echo, and you'd expect that bridge will have no delamination, but there was 35% delamination in that deck. It's worrisome when you see a new deck. We are assuming full composite action in design. That's a disaster waiting to happen if you have 35% delamination. Some of the delamination is within the girder interface with the girder, with the deck, and some other places is a midspan. Doesn't make any sense why there will be that kind of delamination. So it's something to investigate and find answer. Why is it a constructability issue? Is it a material issue? The work needs to be done because this is a very popular type of bridge, especially in Texas.
Yeah, sounds good. Thank you, Nur.